Alrighty, 6.4, heat capacity and calorimetry. So you're going to be learning about these two concepts. And with these two concepts, we're going to be doing two different labs. So there's one lab that I've been alluding to with some students with the fire. And then the other lab is going to be calorimetry, which we'll talk about and discuss the different parts of it before we actually do the lab. So in calorimetry experiments, we have something that looks like this drawing here. Our things are a little fancier, so we don't have styrofoam cups. We're actually going to use an actual calorimeter, and so we're going to be using similar situations, but you should be able to recognize what the, more DIY looking one is, because sometimes the DIY one is referenced on College Board questions, so it really depends. And so we talked about this earlier, where we cannot directly measure the enthalpy of the system, the delta H, the final and initial. We talked about how in solutions, when we mix them up together, we're measuring the surrounding waters, but not the actual reactants reacting to each other to make whatever product they're making. And so, in order to find out the heat energy involved for a reaction, we measure that surrounding of that reaction. So, we find that temperature change of that surrounding. We're losing or gaining heat depending on what's happening. And then we use that information to apply it to the actual reaction itself. And so calorimetry experiments is measuring that delta H. And so if possible, we would like to do a controlled system where we have it insulated, and so there would be no heat escaping or being entered in. We would have no mass change. That would be the perfect world scenario. So it's going to be perfectly closed and controlled. Now, obviously, we can't perfectly do that, but we try our best with what we got. And so we're going to be mimicking that in our lab to the best of our abilities. And so typically in high school, we would use the coffee cup calorimetry. So again, if we're looking at this picture here, you can see that we would have coffee cups that are stacked on top of each other. We would have whatever reaction we're doing in here, and then the thermometer to measure the heat change of the water, and then we're stirring it with, a stir, because remember, you don't stir with a thermometer. And then we would have a top to be as insulated as possible, and then we would try to control as many variables. But because of my class, we have calorimetry like system things, and so we'll be able to use those. And so usually water is measured because we're mixing different solutions. We might be measuring something else. It really depends on what we're measuring, but in this case, it will be solutions mixing together. And so as a reminder, because it is water, 1 milliliter corresponds to 1 gram. If it was something else that was the solvent, then that would not be the case. But because 1 mil is 1 gram, you're good to go for that. We also like to control the fact it's a constant pressure. So we want to make sure that the pressure is constant. Now, we don't have to worry about that because pressure is always going to be constant in the classroom. It's always going to be, standard pressure because we're on we're not high on a mountain or like lower than water level. So we're good there. Cool. And so when heat is being transferred between two different bodies, so like two different things touching each other, whatever that may be, we use the equation Q equals MCAT. So for those of you that had me for Gen Chem, this was the beginning of the year for Gen Chem. And so you should be able to just plug and chug with this equation. And so if we are heating up something that's cooler from a warmer thing, then we can see that transfer by using Q equals MCAT between the two different systems. And so on the bottom of the constant equation sheet, we have the equation there and then what the variables are. So make sure you can identify where that is and be able to use it so you don't have to just memorize it. I mean, granted, I memorized Q equals MCAT because it sounds like a cat, so easy peasy, but make sure you can locate it and know what all the variables mean. Now, one thing I want to make very, very, very clear is that Q does not equal delta H. Q is heat, delta H is the change of heat, so you want to be very, very careful. Q can't be negative because remember that heat energy cannot be negative. If you calculated a negative delta H, again, that's only talking about if it is moving in a certain direction, so the magnitude of the energy. And so here is the constant equation sheet at the very bottom of that second page. And so you see under thermodynamics is Q equals MCAT, and you can see what each of the letters mean on the right side. And so you don't have to memorize it. Granted, you could just remember and it works out, but there we go. And so we have several units for these. And so we have our mass is grams, our Q is joules usually, delta T might be in Kelvin or degrees Celsius, it really depends, and C has hella units as I said on the slides. Now, you don't need to memorize the units for C. We have the equation, so Minnie, your turn. Why don't we need to memorize the units for C? Think about it, write it down, and then I'll answer in 3, 2, 1. Because we have an equation. You could solve for C, for Q equals MCAT, and then you can get the units from there. So for example, I'll do that off to the side here. We have Q equals MC delta T. And so if I solve for C, I divide both sides by M delta T, like so. And so when I do that, I get C is equal Q M delta T. And so if I look at the units of each of these, I'll get the units for C. And so Q is heat, so heat's in joules usually, so J. And then our M is mass, so that's grams. And our delta T is either Kelvin or degrees Celsius, it depends. And so you would have that. And so there's my units for C. Don't need to memorize it, just solve for it. Makes it so much easier. So there we go. Alrighty, so specific heat, like what the heck is that? We have specific heat capacity, we have specific heat. So let's talk about that real quick. And so here's our definition. So we have a certain amount of energy, and we're raising the temperature of a gram of something by 1 degree. And so we're always dealing with degrees Celsius or Kelvin because they're 1 to 1. We're not dealing with Fahrenheit. And so it's the energy involved to raise it that degree. But like, what does that even mean? Like, what kind of definition is that, right? And so if I think about it, think about how much the substance can change in temperature. So can it change quickly, or does it take forever to change in temperature, depending on how much energy you're inputting, right? And so let's think about some examples of this. So if I have a large specific heat, so a big number, that means we're a good insulator. A good insulator means that it's good at keeping heat, because a large specific heat, if we go back to the units from earlier, so let me just write that down earlier, so J per G degrees Celsius, if I have a big number, that means the amount of energy needed to raise the temperature by a degree of just 1 gram of the substance, you need hella energy. And so if I need hella energy in order to raise it just 1 degree, then that means it's a good insulator. It's going to keep heat very well. If I have a small specific heat, then it'll be a good conductor of heat. It's good at letting heat go for this scenario, because if I have a small number, that means I don't need a lot of energy here, and so that corresponds to being a good conductor. So let's think of some real life examples. So water has a specific heat of 4.184 joules per gram degrees Celsius. And so that's a pretty big number, actually. And so when I think of some examples of this, let's think of water. So imagine you have a pot of water on the stove, and you heat up that bad boy to maximum heat. But it still takes a while for water to boil. Like if you literally watch water boil and do not do anything else, it takes forever to heat up. And so that's because it has a large specific heat. It's good at keeping heat, like really well. And so if I raise it to some temperature, so if I raise it to like 90 or whatever, then it's good at keeping that heat to 90. It will not decrease quickly enough if you are at, average room temp otherwise. Another real life example of this is fish in a pond. Fish in a pond, if we have a pond outside And between night and day, the temperature of that pond will not increase or decrease that much, assuming like normal weather conditions. And so the fish in the pond are going to live just fine. Because of the high specific heat of the water, water's holding that temperature really well, whatever temperature that water is at. And so the fish are not going to go crazy because the temperature change is not going to be very different between day and night. So even if there's not a lot of sunlight shining on that water, at nighttime, it's still not going to lose that much heat during the night versus the day when it is gaining heat from the sun. And so fish and other wildlife, they're adapted to the fact that water will not change significantly between night and day, and so they're able to live in water like that. So despite the weather changes that we might have, the water itself probably will not increase or decrease if it's, consistent weather conditions. Alrighty, so here's an example problem. So go ahead and read it to yourself real quick before I talk about it. Cool. So anytime you have a word problem, best way to solve these is doing the guess method. So list your givens and unknowns. And so I'm not going to write down my givens and unknowns. I'm just going to write it on the actual problem. If I were to take the AP Chem test now, I would literally just circle the unknown and like put what it equals to or the knowns in the problem rather than rewriting it fully. And so let's go ahead and look at our givens. So we have our 16.76 kilojoules. So thinking about the units, that means that's going to be our Q. And so if there is 5 kilograms, so kilograms is going to be our mass in the pot, and the temperature is raised, so it's raised by 80 degrees or 80 Kelvin, so that's going to be our delta T because it was raised by that. We don't know the initial final, but we know it was raised by that, so that's why it's delta T. What is the specific heat of water? So specific heat of water, we have, that's C. So C equals question mark. And so we're going to go ahead and solve the problem. So we have Q equals MCAT. And so I need C by itself, so I'm going to divide both sides by M delta T. And so I have my C equals Q divided by M delta T. And so I'm going to go ahead and plug in my values. So 1676 kilojoules. And then I have my mass is 5 kilograms. And then I have my delta T being 80. And so notice I didn't convert my units. I left it kilojoules and kilograms. And that's because kilos cancel out. Like if I were to convert this to joules and then convert this to grams, it's by a factor of 1,000 for both. So essentially I would have 1,000 more on the top and 1,000 more on the bottom, so they would have canceled out anyway. So why am I going to convert it when those are going to cancel out anyway? So they're canceling out, and then when I do that math, I should be getting the specific heat that I mentioned earlier, maybe slightly off depending on rounding errors. So here's the specific heat from earlier. It's degrees Celsius in this one, but this is in Kelvin. And so when I plug that into my calculator, again, I should have a number similar to that. So I'm going to check on my calculator real quick. And so when I calculate that on my calculator, I get 4.19 J per G Kelvin. So notice, same thing. And the reason it's the same between the degree Celsius and the Kelvin is, again, Kelvin and Celsius is just 1-to-1. It's just that one formula adding 273, and then boom, you got your Kelvin, right? And so, because everything's 1-to-1, your ratio for your specific heat is going to be the same, which is why I got the same answer. So when you're doing these kind of problems, identify your givens, identify your unknowns, sub and solve, boom. So what you're going to do is you're going to do this your turn. So again, you have this on your paper, identify your givens and unknowns. That helps a lot. See what you're trying to solve for. And then here's the answer. So I gave you the answer already. And so go ahead and pause this video and try it out. And then I'm going to show you how to do it in 5, 4, 3, 2, 1. All right, here we go. So here's our givens and unknowns, so I'm not going to explain that whole thing. I calculated delta T already in the givens because it technically is a given. And so then I am solving for Q because it says calculate amount of energy absorbed by water. And so I literally just plug in. I didn't have to manipulate the equation at all. Multiply everybody out. Everyone cancels out except joules. Got my joules. And, oh, I actually didn't check my sig figs. Let's check real quick. 4, 3, 3. Yep, so it's going to be 3 sig figs at the end. And so that's why I rounded there. Perfect. All right. So there are 2 things that might be a little confusing. So I like to talk about both of them to make sure that we understand the differences between the 2. They are almost the same, just slightly off. And so for specific heat capacity, it's the energy of a gram of the substance by a degree. Versus the other guy, it's going to be something else. Well, molar, you can assume, right? And so the unit for specific heat is J per G degrees Celsius or Kelvin, one or the other, who cares? And so I got the units from isolating C, easy peasy. Now, molar heat capacity is, as expected with the name, a mole of the substance. So the units are usually kilojoules mole K. Again, you could switch the K with degrees Celsius, but you can change these units depending on what's given. So sometimes it's joules, again, could also be degrees Celsius. So be very, very careful about units. Very easy to mess those up. Yeah, perfect. All right, so in this experiment, you do stuff, right? And so we're measuring that heat flow. So we're checking heat gained from the system, versus heat lost to the surroundings or vice versa. So if the system gained energy, that means the surrounding lost energy. And so if the system lost heat, then the surroundings gained heat. And so we can relate those 2 things together. So the reason why we can connect those two things together is because the first law of thermo that we talked about earlier. Energy is conserved. It's neither created nor destroyed. So if something's gaining, something's losing. It cannot disappear. And so heat gained equals heat lost. Again, conserved. And so because we can't directly measure the system, we measure the surroundings. Again, for this experiment, it would be measuring the water with that thermometer. And so because water is commonly used, we're going to be using that specific heat a lot. So keep that in your back pocket so you should be able to use that. Normally it's defined on an FRQ, but in case it's not, I would recommend remembering it. So remember that because it's water is used almost all the time. And so here is a multi-step problem. So the first question is pretty easy. How much energy is required to heat up water? And so we have a specific heat, we have our mass, 100 milliliters converts to 100 grams because 1 milliliter is 1 gram, we talked about that earlier. And then I have my delta T from just, final minus initial. And so I'm calculating my unknown Q, and so I plugged and chugged and I got my Q. Cool. So now let's talk about the second question. So this would be like an FRQ part B or something. And so let's go ahead and read that real quick. Cool. So we know that a piece of metal is hot. It's at 100 degrees Celsius. It has a mass. And we're going to heat up that water. Because notice the water was at 27, right? And so we're going to we heated up that water 2 degrees by using the antimony. We're going to figure out the specific heat of that metal. So a couple hints. So first law of thermo, if we have the heat of the water, then we can get the heat of the antimony. Because remember, thermal equilibrium, they're both touching each other. And so I can relate those 2 things together. I also have the molar mass just to save you time so you didn't have to find it on your PT. And so here's a drawing because some people are more visual, right? And so we have this water here. And so we have an antimony that we threw in there. And so the antimony again was hot. And so that means that heat is going to be leaving the antimony and going into the water. And so the water got heated up. It got heated up by 2 degrees according to my calculations earlier. And so we're going to keep that in mind as we go through this. Cool. Oops. Go away. Okay, there we go. And so here's my givens. I'm just listing my givens again. I could have just written it on the problem itself like how I did it before. But here are givens. And so notice I actually have my T-final. I have the fact it was 27 degrees Celsius because remember, this piece of metal heated up that water. And so to go back to the first question, the water went to 27 degrees. It was 25, then it became 27 by this piece of metal that we threw in there in order to raise it 2 degrees because of thermal equilibrium. And so I have my delta T here, so I calculated it right here. Perfect. And so my unknown, or before I do my unknown, so here's law of thermo, right? And so the heat of the water from the calculation earlier equals the opposite heat of metal. Now again, heat cannot be negative. The negative is just corresponding to the fact that heat is being lost to the water. So we're keeping that negative sign to know the direction. But technically there is no negative joules, so remember that. But we do use the negative negative for stuff. And so we need to find our C. We also need to find our molar heat capacity, which unfortunately could also go by C. And so those are the 2 questions we are answering. Okay. So I solve for C. We're using Q equals MCAT. I'm going to plug in our values. And so then I get my specific heat. Easy peasy. And so in order to calculate molar heat capacity, I'm going to take that. I'm going to convert the grams to moles using the molar mass. And then I plug and chug and I get 26. So easy peasy. You just convert to moles instead of grams. That's all. So be sure you can use the molar mass of a substance if you need to. Again, make sure to understand the thermal equilibrium happening in this problem. So just to go back to the previous slide real quick. Drawing pictures helps a lot. If you get super lost on a problem, drawing a picture and literally drawing what is happening helps visualize what is happening. And so that's why I have this picture here where I drew arrows, because that's the heat escaping. You can even label it heat escaping so you know what's happening. And so it just makes it easier to understand the problems with a diagram. All right. Cool. So here is your turn. So go ahead and read the problem. Try it yourself. I have the answer right there. And then I'm going to go over it in 5, 4, 3, 2, 1. Here we go. So there's a lot of work here. This is combining the 2 things that we did earlier where it was 2 different problems, but this is thrown into one. And so the best way to do this is to organize your givens. And so I listed my givens of the metal. That's why I put subscript metal. And so I have my metal mass, I have my temperature change, cool, and then I also have my water, because water reached 27.8. It was initially at 23.7, and so there we go. Then I have my specific heat. Now remember, thermal equilibrium, the heats are going to equal the same thing. We use the negative sign to correspond to, the direction it's going, just for easy math purposes. And so here's our sub and solve. So we're doing the water first. So I substituted all the values for water. I got my answer. And so I can relate that to the metal. And so I'm going to go ahead and put the negative metal here for the Q. And so then I literally just plug and chug. I get my specific heat. So if you're ever lost, again, doing the guess method where you organize all your information helps a lot. Drawing a picture of this scenario would also help, similarly to the example earlier. Cool. Okay, so thing to notice. The thermal energy, which was the Q, in our calculations does not produce the same temperature difference between the water and the metal pieces. And that's because they have different heat capacities. So just to go back to the ones over here. If I look at the heat capacity of water, that's 4.184 J per G degree Celsius versus 0.402. You don't need that much energy to change a degree. Versus in water, you need way more because it's 4 versus 0.4. So, a degree of 10 or a factor of 10 is a lot. So be very mindful about stuff like that. Cool. And so molar enthalpy, it's about a mole. There's different things with molar enthalpy that we can do. So, for example, we can use molar enthalpy to talk about compounds if we had pure substances. So when I talk about a salt, I'm talking about any ionic salt. And so I just default to NaCl because we love NaCl. And so if I was trying to make sodium chloride by taking sodium and taking chlorine and smashing them together to make sodium chloride, I can find out how much energy is involved in that by using molar enthalpy. So same thing, I can use molar enthalpy for phase changes. So if I'm going from liquid to gas or gas to liquid or solid to liquid or whatever phase change I'm going to, I can use molar enthalpy to calculate that. And then of course I can also calculate reaction enthalpy. And so let's think about molar enthalpy in terms of solution making. So here is a question. So go ahead and read that question real quick. Okay, and so I highlighted what we're solving for just to save time. And also see this note here, you want to make sure you understand the concept of the math, not just the math. Because the math is easy. I mean, math is just algebra. But like knowing what is happening, why it's happening, that kind of thing, that's the biggest things that you should know for these problems in case they ask some reasoning questions on an FRQ. So potassium nitrate, you should have memorized your polyatomics, and you can look up potassium as K, so +1 - 1, so there's our KNO3. And so our delta H for the solution is related to our Q. We can see that it's going to be exothermic because we're seeing the water. Yeah, sure. Wait, is it? Hold on. Okay, whatever. I paused it to like check what I was talking about. I'm like, whatever, it's fine. Okay, so we're doing a thermal equilibrium thing with making potassium nitrate. So again, we're making a solution. So remember that making a solution is also known as solvation. So be sure you know that. And so we're gonna go ahead and do similar math to before. So we're taking the solution. We have Q equals MCAT of the solution that we're making, right? And so we're going to assume that the solution specific heat is the same as water because all solutions that we usually work with is made out of water being the solvent. And so we're just going to assume that the whole solvent is specific heat is the same as water's. Now, technically it wouldn't be, but because there's so much water, it's dang near that anyway, so we're just going to use that, and so the AP test is going to do similar, unless they give you the specific heat. And so I'm going to go ahead and calculate my delta T of the water, because I know that, so there we go. And so my delta T of the solution is going to be the opposite, because we're talking about the dissolving of potassium nitrate. So remember, I can calculate my delta T but of the water, but that doesn't mean I am getting the actual solutions. And so the solution is the opposite, because if water is gaining heat, then the making of the solution is losing heat. Or if the water is losing heat, then the opposite is true for solution making. So when I'm dissolving KNO3, it gained 3.3 degrees Celsius. The water lost 3.3 degrees. So be mindful of that. Cool. Alrighty. So the mass of the solution, well, we have a mix of the water and the potassium nitrate. So notice I highlighted that because that's very important when calculating solution making, because both of them have mass, so they both are part of the solution. So we have water, a lot of it, and then we have some potassium nitrate, and we mix them together to get that total mass. And so I'm going to calculate the heat for the solution. And so you can see here I have my mass of the solution, I have my specific heat that I roughly estimated to be the same as water, and then I have the change of temp, which was 3.3. And so I calculate that, cancel out units, I get my joules, which makes sense for Q. And so delta H, because we're getting molar enthalpy, is going to be kilojoules per mole, usually. Could be other units too, but, we're just going to stick to that. And so I'm going to convert joules to kilojoules. You convert it however you want. Boom, there it is. Just make sure you can convert. And then we need the moles of the salt. So I have the grams of the salt. I'm going to calculate the moles using the molar mass of KNO3. So here's our molar mass. I totally forgot to put this KNO3 here, so it cancels out. But whatever, grams cancel out. Got my moles here, calculating my moles. And so then I just input it in delta H equals kJ per mole. So I got my kilojoules, I got my moles, boom. And then positive number makes sense. Cool. So there we go. So remember, the solution gained heat, which is positive. The water lost heat because it was negative. So just remember that exo-endo stuff. The temperature of the water drops, so water had to lose energy to make solution, aka, lost heat. So lost heat is exo. So be very careful about that. That's what I was trying to talk about earlier, and then I'm like, wait, pause. Oh, wait, I'll just talk about it later. So I'm talking about it now. There. So be very, very careful. It is very confusing sometimes to see the exo-endo stuff, so just be very mindful of who is negative, who is positive for the purposes of the direction of the heat. Alrighty, so here's a quick little thought experiment. You do not need to math or anything. You got to think of an experiment, right? So we calculated molar enthalpy in the example earlier. The actual molar enthalpy for potassium nitrate is 34.89 though. And so why is the experimental value less? Think of what errors could have been made while doing it. So go ahead and think about that. And then I will mention this in 5, 4, 3, 2, 1. All right. So an example of this is maybe this making of the salt solution was not in an insulated system. So we talked about like an open one or a closed one. So heat potentially could have been lost there. The energy could have been absorbed by other surroundings other than water. So again, because it's not well insulated, it might have gone into the atmosphere, the heat, for example. So those are some examples of where it could have gone wrong. Cool. So overall, you should know what is the system versus the surroundings. So when quote-unquote Q is negative, use it for the math purposes, but know what the heck it means when Q is a negative number, because there's no such thing as negative heat. Use the first law of thermo, use thermal equilibrium, use Q equals MCAT, plug and chug, easy peasy. Now again, this is slightly different than Gen Chem because we're dealing with more thermal equilibrium stuff. So just be very mindful about that when doing these calculations. Alrighty, that's it from me. Bye!